This is Yiwei, and this is the report video for my optimization class project. The project is about the optimization of a world travel routine. In the real-world model, the objective of the problem is to maximize the number of cities a traveler can visit during a world trip. The variable is the number of cities, and the constraints for the problem is the cost, including time and money. The number of cities can potentially affect the total cost in multiple ways. The first step I took is to simplify the problem and model it as a computable mathematical model. The core part of the problem is to solve a typical traveling salesman problem, which can be done by using the Miller-Tucker-Zemlin formulation and the integer linear programming function in MATLAB. The decision variables are binary and associated with each trip, with each one represents a trip that exists on the tour, and each zero represents a trip that is not on the tour. Then the total distance can be minimized as shown in the objective function. The major difference between my problem and a typical TSP is that in my problem, I have to select M cities out of N cities and search out the possible combinations of M cities. Then I iterate through each combination to find the optimal routine. For example, if I am to pick 2 cities from 3, I will have 3 iterations and thus 3 optimal routines. Since both money cost and time cost during flight are based on distances, I simplified the weights by representing it by distances. The distances are calculated using geographical coordinates, while assuming the Earth is flat. Therefore, the weights for the edges can be regarded as numbers showing how costful the edges are. Then I determined the vertex weights by myself according to the edge weights. The objective of the simplified problem then becomes maximizing M while keeping the minimum cost below my budget. The algorithm for solving the problem is shown as following. Firstly, I pick M cities from N cities and get all the combinations of these M cities, starting from M equals 3. Then I run the TSP solver for each combination and record all the optimum results. The minimum value of all the optimal results will be the final value to be compared with my budget. If the value doesn't exceed my budget, I will increase the number of cities M by 1, then run the process again. I prepared a list of 11 cities that can be chosen for the trip, and I picked 3 optimal routine results and visualized them on graphs. The 3 graphs represent the optimal routine with M equals 10, M equals 3, and M equals 6, respectively. I also recorded all the final total weight values for each M. The numbers in the table are to be compared with my budget, which I don't have for now, since the numbers are just weights instead of time or money. As I mentioned in previous sections, the weights were determined to show cost of time and money, but they can only be used to intuitively show the cost, not quantitatively. So a larger value simply means a larger cost. Another aspect of the programming I want to mention is the running time. The number of cities on the list can affect the running time significantly. Initially, I used N equals 11, and the longest running time was about 1 minute. Then I tried N equals 13. It increased to about 3 minutes. So it can be seen that if I continue to increase N, the running time will increase significantly. There are improvements that can be made. Firstly, my program could not increase M by itself, so I have to increase M manually each time. Secondly, I can improve the program by actually assigning weights with money cost or time cost, so that the results would make more sense in real world. Thank you for watching.